so much. Yeah, so my name is Kashif. I'm work at Hugging Face, and I'm really honored to be presenting to you all at Tsinghua University. Thank you so much once again for the invitation. So I wanted to talk about reinforcement learning for human preferences in the context of language modeling. And in particular, I wanted to talk about some recent trends in this area. But I'll start by introducing you to the problem of alignment and alignment fine-tuning, and give many examples, both from a theoretical perspective, and also then in the second half, I'll talk more about the practical aspects of how to train, how to run these algorithms on your own data as well. So both theoretical and practical parts. And I'll leave a lot of time for questions. And I also want, if you have questions, to just interrupt me and ask. Okay, so with that, I guess we can get started. So I don't know if you remember in the past, the Microsoft Office Assistant had like this intelligent user interface to Microsoft products, and it assisted users by way of very helpful or not so helpful suggestions. And what has happened in the last few days is something similar as well. As you know, with the use of language models, they've become extremely good at solving a lot of practical problems, like helping with answering some complex questions, which is, for example, here, it's quite a complex question to write a regex in Python, and this ability to solve such complex problems has given rise to the popularity of such models and services in a lot of domains, and caused language models to become very viral these days. Despite their successes, in practice, these raw LLMs also have a lot of problems, like getting up-to-date knowledge, getting correct, consistent answers that is not some random hallucination, and of course the problem of generating appropriate responses when interacting with humans. And so the popularity of ChatGPT in some sense is really attributed to how it will, for example, not give responses to questions that are somewhat ethically questionable or somewhat secret, for example. And the way this is done is via the process of what's called alignment, which is the topic of this part of the course. Right? And please, if you have questions, just let me know. So a solution, as I said, to generating appropriate answers is alignment. So what is alignment? Well, alignment is actually the process of encoding some values and goals into a language model to make them as helpful or safe or reliable as possible. And through alignment, one can tailor these AI models to follow their business rules and policies. So I'm going to highlight the issues by this example here about why one would need alignment. With respect to this prompt, is pineapple on pizza a crime? So maybe in China it's okay. Maybe it's okay to have a pineapple on pizza, but maybe if one was to ask this in, say, Italy, then you would get maybe a different response. And so the big issue with using just a pre-trained base model is that it has been trained on just the next token prediction task. And so if you were to ask a raw base language model this question, the answer that you might get might be just some completion of this sentence, given some past training data that it had seen during training. So in this case of our question on pineapple pizza, because of this autocomplete complete kind of nature of how it was trained, the text will be something potentially unrelated uh, and have something from the uh, training data set here. And so it's not very helpful at this stage. So given this drawback of pre-trained language models, one typically needs to do what's called supervised fine-tuning. So in this case, if we require question answering, then one can train it on human or synthetic generated responses in some appropriate manner. So after doing supervised fine-tuning, if, for example, the answer to the prompt might be something like, is adding adding pineapple on pizza is a crime as a topping and is a criminal act under the Geneva Convention, for example. And this is because it could be because in the training data, the person who annotated say a pizza on pineapple type questions maybe doesn't really like pizza on pineapple, and so most of the question answer training sets here would be kind of biased towards not liking pineapple on pizza, and then maybe because of the word crime, it kind of associates it with much more serious things than just pineapple on pizza. So here again, after doing fine tuning, the model is kind of responding with some bias to an inappropriate answer based on the biases in some sense of the person who annotated the question answer data sets. Um, so if, for example, we were a pizza company, such a chatbot would also not be appropriate, right? So alignment offers a way to move the LLM closer to like how humans, like how normal humans would essentially answer such a question, or some professional or friendly person would answer such a question. And at a high level, what we're essentially trying to do is we're trying to teach the model that given such a prompt, we want our answer that says yes, it is a crime, to somehow be marked in some sense with a preference which is negative, and we want our answer that no, this is not a crime, to be marked with a preference that is positive. So at a high level, what we want is we want to teach our LLM that the preferred response, in this case, the no, should be more a likely output than the unpreferred one, given such a question, given such a prompt. So essentially, we want to learn the probability that the preferred response is generated much more often than the rejected one. Okay, so and so if we were to do that after training on such a data set, we end up with models like ChatGPT or Mistral and so forth. Its completions are much more human-like and potentially useful for tasks like summarization. So in this example now, after doing such a process, the answer might be much more appropriate, like no, adding pineapple as a topping on pizza is not a crime. It's just a matter of personal preference and taste, which is a much more appropriate answer and much more professional and friendly. And so doing alignment in some sense makes these language models much more useful in the real world situation as well. Right. So how was this alignment done? Let me show you how. Sorry, any questions? No. Are there any questions? No. No. Okay. So the original approach was pioneered by OpenAI, which they called RLHF, which is reinforcement learning with human preferences. And it's essentially a multi-step approach, where in the first step we do so in the first step we do what's called supervised fine-tuning using the data they've gathered from human annotators. So these human annotators have created high quality examples of questions and answers. And OpenAI fine-tuned a variety of GPT models on this data. So in detail, in this phase, one is given, say, 10 to 100,000 demonstrations that are diverse and of high quality, and they train then models on these question and answers. In fact, not just one model, but multiple models. And the resulting models are what's called proto-chat models. They can follow instructions, they can write code, but not to a good degree, as you can imagine. And the typical failure modes of these models are usually from the inability to model the data distribution. And so remember, this work was from 2020 to and 2022. So that's the first step. Just as an aside, when these papers came out on the open source side, there weren't many open source, data sets for such supervised fine tuning. But this has changed these days. We have a number of high quality data sets to be able to convert any base model into a chat model, and I've highlighted a few data sets here, which are all in the open. And you can use them to also do this first step of supervised fine-tuning on any model. Okay, so that's just an aside. So step 2. So what OpenAI did next is to take their chat model and try to model human preferences. So what they did is they took a collection of prompts and got a variety of responses from their chat model. So here's their prompts, and they got many responses from their trained models, So response A, B, C, and D, for example, to a particular question. Then a new type of model, and of course, then what they did was they took humans to judge which of these responses was the best, and so forth. So they ranked the responses from best to worst, and collected such a data set. Then, given such a data set, they trained a new type of model called a reward model that essentially predicts the score of a response as a regression task from given these labels as ground truth labels to the responses. And then at inference time, such a reward model can be used to get scores for unseen responses. And these scores can be used to then rate and rank responses given any unseen prompt and response. And the reward model just gives scores to the responses given and takes the responses generated by some given some prompt and response, you output a score, and given that score you can rank then the responses from best to worst. So essentially these reward models are encoding the human preferences that were collected via this first step here, right? And the result is a reward model, which is essentially just a binary classifier that can score some model's output according to human preferences. And of course, in the open source setting these days, there's many such data sets which you can use to train a reward model. And for example, if you look at the Llama 2 paper, it used both open source collections of such data sets, as well as internal ones as well. And for example, the Llama 2 reward model had around 3 million such preference pairs that they used to train their reward model. But as I said, there's many open source, open data sets to train your own reward model, and that is what I want to highlight here. That there are quite a lot of these paired ranked data sets, which can be used to train a reward model. So back to reinforcement learning with the human feedback, we now have a chat model, we now have a reward model, and the final step is to combine these two to create a new chat model that has learned to encode the signal from the reward model. And the way OpenAI did it is to use the machinery, as I said, of reinforcement learning. But the basic idea is very simple. Is essentially they give a prompt, the model outputs some response, the model that we're trying to align outputs some response. The reward model is used as a signal to nudge the weights of the chat model to generate high scoring responses and to discourage the model from low scoring responses. So it gets punished if the response according to the reward model is bad, and it gets rewarded if the response is good, right? Via this score here of the output in this kind of loop here. And this is done using the machinery of reinforcement learning. And the result of doing this at scale is essentially ChatGPT or Anthropic's, for example, Claude model as well. So essentially, is taking step 3 and scaling it to much larger base and reward models. Mathematically, the idea here is that we're trying to maximize the reward. So given some prompt, X is the prompt, Y is the response, right? For, X coming from our data set, we're trying to maximize the reward of the prompt and the response from the language model via this external reward model. So that becomes our loss in some sense. But at the same time, there is the second part of the loss here, which is called the KL penalty, with a beta term here. The beta is controlling, in some sense, the strength of this KL penalty. So what is this KL penalty? Well, if we didn't have the scale penalty, what can potentially happen is that the reward, our base model, our model that we're trying to learn, the pi theta, will start to do something what's called reward hacking, meaning the chat model will learn that if it outputs some certain tokens or some certain emojis or certain characters or generates very large sequences of maybe some random things, the reward model will give a very high score, because remember, the reward model is also a neural network and it's not perfect. And so the model that just without the KL penalty term will learn to exploit the weaknesses of the reward model and start to generate maybe random things which will not be too useful, even if they generate very high reward. So the second part here is called the KL penalty. With respect to the weight beta, that basically measures the distance between the model that we're currently trying to train and a reference model, right? So the reference model is typically the initial chat model before alignment. So what this is in some sense doing is that it's forcing the model to together with increasing the reward, it's trying to force the model to not be too far away from a chat model, right? So we still want our model to be a language model, but a language model that is maximizing the reward with respect to the reward model. So with these two objectives and the RL algorithm like PPO, one can get something which is very performant and aligned. But in practice, however, there are certain challenges here associated with this algorithm. And those of you who have done any RL can perhaps relate to this. RL schemes typically tend to be very unstable. They are very finicky with respect to the hyperparameters. At each step, we need to generate, at each step of training, we need to generate output for the reward model. The algorithm tends to also be slow, especially when these language models become very large. And more importantly, this scheme now has three very large language models that we need to somehow juggle when training. We have the initial model, we have the reference model, which essentially is a copy of the initial model, large language model, and then we have the large reward model as well. And so to do this at scale with very, very large language models becomes much more of an engineering challenge than a mathematical one. And trying to get this running consistently without crashing is art unto itself. So doing anything at scales larger than say 10 billion parameters or more gets extremely challenging. There's also a blog post on how many of these hyperparameters in these algorithms change the performance of these resulting models as well. And you'll see in the blog post if you look at it that changing just one parameter of the Adam optimizer causes drastic changes in the resulting aligned model. So it's very, very somewhat unstable. Any questions here? Okay. So the higher level question in some sense is, do we really need the machinery of RL to do alignment? Which is what I want to explore next. And that is done. So the idea, of course, is no, we don't need it. We don't need. So in a talk, whenever there's a question, in the middle answer is usually no. Of course, in this case, this paper on direct preference optimization essentially says no, we don't need this whole machinery of reinforcement learning. One can essentially reparameterize the reinforcement learning objective from the reward function to the and instead use the language model itself. And this way, we don't need to train a reward model, and we don't need to use it in the alignment phase. So at a very high level, the language model itself acts both as a language model that we're trying to train, and also as a way to get reward as well, instead of a explicit reward model. So let's look at how this what the loss is here, and how it, and some gets intuition about what it's doing. So the main loss that the paper is trying to maximize is given by this formula here. Let's go through it. So we're trying to maximize with respect to our language model pi here. And we're given, as I said, preference data, which is a prompt, the initial question, and two answers, right? One answer is labeled as the winning answer, the preferred one, and the second one is the unpreferred. And then the loss, of course, is the log sigmoid with respect to these log ratios of the preferred response and the unpreferred response. Okay. So let me start by giving you some intuition here. So as I said, in our example, we have our X, which is our prompt, is pineapple on pizza crime, and then we have our good response and our bad response. So here's our good response, no, and our bad response, or the unpreferred response, is called yes here. So this is represented by this tuple sampled from our training data. Given this, we're going to compute two things. Basically, the log probabilities that the model is able to predict the chosen response as a ratio, where the bottom probabilities are the KL term forcing. So this ratio, in some sense, when you try to maximize it, it's forcing, because the log of something is just a difference. So it's log probabilities. The difference of these log probabilities, it's essentially forcing this thing to be somehow close to the log probabilities with respect to the reference model. So this here is acting like the KL term from the RLHF objective. And here, this one is the model that we're trying to optimize, remember. And so, and this is the frozen reference model with respect to the winning output. The second term is essentially the same. It's computing these log probabilities of the undesired response, again as a ratio of the chosen of the model that we're trying to optimize and the reference model. And so if we stick these two terms together with a minus sign here and weighting parameter beta inside the sigmoid, we're essentially what we're saying is we're rewarding the model to predict the chosen responses and giving high log probabilities to the chosen, and in some sense low log probabilities to the undesired one. If, for example, this term here, the undesired one became larger than the small one, because of the log sigmoid, we incur a penalty. So we are punishing the model when this second term is larger than the first term. And so the great thing here, in some sense, is that this whole objective is a differentiable loss. We can just use backpropagation to optimize our model directly, and this is really, really simple. So once the tensors are prepared properly in PyTorch, the loss can be written in these 5 or 6 lines of code. And so you directly just prepare these log probabilities, and then with respect to the beta, which is a hyperparameter, and just directly backpropagate and maximize this loss. Any questions here about the intuition here of these two terms? Well, I'll show more examples of this in a second. So in terms of how well it performs, if you read the paper, this loss in some sense is much more robust to once trained. It's, for example, if you look at the second plot here, once trained, the performance of this method with respect to the reinforcement learning is much more robust to say the sampling as well, and it's it achieves a much more higher, in some sense, reward, because that's what we're doing directly with this loss, with versus the reinforcement learning method here. So um, just to for you to get some more intuition about what this loss is doing, if with respect to the hyperparameter beta, if we look at the derivative of the loss, we can get even some more intuition. So the derivative has three terms, where the first one is a weighing factor. Here's the weighing factor. So this weighting factor measures the difference between the implicit reward of getting the correct versus incorrect response. So essentially, the difference between the ratios. So this is the weight in some sense. So if this was, if the wrong, if the undesired response had a higher value here, so this weighing factor would be large because of the sigmoid, and then this weighing factor is used then in this difference, and the difference in some sense is essentially increasing. The first term here increases the likelihood of the of the of the chosen response, and then decreases the likelihood of the undesired response. So if this was large because this difference was, if the model outputted, say, the undesirable response, then we are punishing, in some sense, the model by increasing the likelihood of this term and decreasing the likelihood of this term even more, because of the sigmoid term here. Right? So, and this beta term actually controls, in some sense, how much we want to push the model to have a margin between the chosen and the undesired responses. So you can see here a plot of this margin as you train for different betas. So as you increase this beta, during the process of training, the difference, like you're pushing the model to the model's weight, so that the log probabilities are getting further between the chosen and the undesired are getting further and further away from each other. So the reason why this beta is important is also something that you need some intuition, and the intuition is that in training data, for example, your chosen and undesirable responses might not be might be imperfect, right? There might be some errors in your data set. So if you if you choose beta to be large, you're essentially saying that you're really sure that in your data set, the chosen and rejected responses are in some sense really correct, and you want them to be very far from each other. However, in real life data sets, that's typically not the case. And in many situations, you don't, it's very difficult to say what is chosen and what is the undesirable response. And therefore, having a smaller beta, in some sense, still pushes the good ones away from the bad ones, but not with such a large margin, because your data set might not be, their training set might not be perfect. So you really need to tune, in some sense, this beta parameter for your data set in order to then get appropriate evaluations. Any questions here? Okay. So in terms of training these models, there are essentially two main libraries to do this: the TRL library from Hugging Face, as well as the axolotl library, which uses the TRL as a wrapper, together with a lot more a lot more kind of helpers here as well. And as you can imagine, the community has now taken these ideas and done a lot of amazing things with it. With the mixtural models being fine-tuned using DPO and so forth. So and also the Yi model from China has been doing DPO as well, and so forth. So a lot of excitement around this kind of model. Just to wrap up this first part, as is common in machine learning, once there's a popular idea, people try to iterate and build on it, and the same has happened with DPO as well. One improvement that has been made was the researchers at DeepMind with IPO, or identity preference optimization. After observing that DPO can end up overfitting, and to prevent that from happening, they add a kind of regularization term in the loss here. On the other end, there's a lot of work on what's called iterative or online DPO methods. Here, the idea is to use a reward model to rank the responses, and you filter then the data set and iteratively train the data that way using DPO. So you do one round of DPO training, then you generate from the model responses. You use a reward model to rank the responses, and then use this new data set to do another round of training as well. And they show that this gives a model that progressively gets better and better. In some sense, this is how Llama 2 was trained as well. The CPO method and the ORPO method further approximate the DPO loss by removing the need for a reference model altogether. And this, again, is impressive, because now you have gotten rid of not only the reward model, but also the reference model as well. And so you have just a single model, which makes it makes scaling it quite easy. Another direction we've seen is the KTO method from Stanford and contextual AI, where they make the important point that if one is to collect preference data, you need to have a prompt and two answers, where one is a desired one and one is the other counterfactual or undesired answer. With human feedback, this is quite expensive exercise, as human annotators need to interact with the chat model and pick out the correct and the incorrect answer, right? By what the KTO authors do is they kind of design the loss so that you only need data that is good and data that is bad. So essentially, prompts and completions that are good, and unrelated prompt and completions that are bad. And so with such a data set, it's much more easier to, number one, it's much easier to collect such data set. And so, and then using this such a data set to do preference tuning is very, very exciting as well. And we will see much more usage of, I believe, KTO in the future as well. All right, so I thought we can have a few questions now, and then I will move on to the more practical side of things, if there are any. Otherwise, we can have maybe a 5-minute break for you to walk around.
Hi, I have a question about the IHF and the DPO. As we can see, the open source community prefer DPO to train the model for the preference learning, but in the original ChatGPT or InstructGPT or or even Llama, they prefer IHF. Which one would be better for better performance? I think as the DPO and the variance of the DPO maybe want to lower down the computational costs for the alignment. So I still wonder why we don't use RHF for better performance.
Yeah, so I believe, yeah, it's a good intuition that for sure, I think people are finding that doing pure RLHF typically gives much better performance or good performance than the preference tuning methods. That is correct. What is happening is that this gap, in some sense, is getting smaller and smaller, especially with the use of iterative or online-based DPO methods or online-based preference tuning methods. And number two, it becomes the gap, in some sense, in performance. And again, performance I'll talk about is also kind of a noisy measure of like how do you evaluate language models, is again somewhat of a noisy thing. But people have been finding that this gap is getting smaller and smaller between TPO based or pure RL based methods and these iterative methods. And so many times for your specific use case, it's much easier and much more accessible to do these kind of methods because of the computational costs that you mentioned, than the more expensive and finicky RL methods. And so people prefer, in some sense, these methods because it just gets them maybe 80 to 90% there, and then maybe that's good enough. But as I said, there's this growing literature of these iterative methods that are also essentially taking the sampling part from the reinforcement learning methods and applying it to these algorithms as well. I don't know.
Okay, thank you.
Yeah.
Thank you for
So it's a trade-off, as you can imagine, between the computational, how much computation you have, how much time you have, and how much you're willing to invest time in trying to get RL working versus just getting almost there with the DPO style of preference tuning methods, where the loss is very simple and the training is very straightforward.
Yeah. Thank you.
Any more questions? Yeah.
I think we can go on the lecture.
We can go on.
Yeah.
Okay, perfect. So now, on the practical side of things, I want to show you how to run fine-tuning and preference optimization on your own data sets, and detail on how to format the data in order to tokenize it for fine-tuning. And I'll then also talk about metrics to evaluate and also show you some things that might go wrong and how to diagnose it from the metrics that you collect. Okay, so let's get started. So the first thing I want to say is that a lot of what I'm talking about in this section is available also as notebooks that you can run. So once you get the slides here, everything that's underlined here is a link to the notebooks on Colab and so forth, as well as the papers that I referenced. Okay, so you can later try this out yourself, hopefully, as well. And so the first step to supervise a fine-tuning for chat model is to find data sets. An example data set is this one, the Ultra Chat 200K. It's a subset of the Ultra Chat dataset that contains two splits. So if you look at it, if you print it, you'll see it has two splits, a training split of 200,000 prompts and completions, and a test split of prompt and completions. Right? So each row, in some sense, is a prompt and completion. So let's have a look at a row. So a row, for example, might be which famous landmark should I visit in London? beyond the usual one, or write a program to implement a dynamic programming algorithm, and so forth. So this will be the prompt. So if you're interested in dataset, as I said, you can find a collection of them, collection of these datasets I've made available as this list of datasets here under this URL here. So as I said, everything underlined is a link. So when you have messages in a dataset, you really need to format them in a specific way for the model to perform fine-tuning. And this is done via something that's called chat templates. And there's a number of different chat templates like ChatML or Llama 2 and the Zephyr chat template. So what is chat template? So let's first dive into that. So the idea of chat template is that you have a sequence of messages that you've been asked to a chatbot, and that these need to be formatted in a way that can be fed to a model for fine-tuning. So you will have like a user asking what is 2 + 2, and then the LLM responding, and then the user asking something again and responding. And so we need to somehow encode such a conversation in some kind of structured way for the model to train with. So the idea is we use different delineated sections of this conversation via different tokens. So an example here is this the start token of a system, and then the end token, and then a start token of a user, and then the user asks something, and then the end token, and then the token of the LLM, here delineated by assistant, and then the end token of that, and again start token of the user, and the user asks something, and so forth. So here, for example, the system prompt is blank. There's nothing in here, right? So let me just briefly say something what the system prompt is. So for example, if you want your chatbot to behave, like if you want to give your chatbot some initial context, for example, you want your chatbot to behave like, someone very polite or professional, you can add that instruction here. Some data sets have a system prompt, and other data sets do not have one. Depending on the data set, there will be something here or nothing here. And then the resulting conversation is also then, dependent on, in some sense, what is in the system prompt, system section here. So the system is essentially primes the language model to what is happening in the conversation. And if there's nothing here, then it's like the default in some sense. So there's a number of chat templates around, and we will recommend the ChatML template to use as the most suitable one for your own work and experiments. So to apply a chat template is also very simple via the latest transformers library. When you just define, in some sense, a Jinja template of this chat template, and then given your message, you can define this. You can define in your tokenizer for your specific model the chat template to be this Jinja template, and then for each example of a prompt and a message, you can just call apply chat template with the message, and it will apply that message, apply that template over your raw training data. And then to then get a chat template version of your dataset, you just call the map function with this helper, apply chat template helper, which runs over each row and each example with your tokenizer, which remember now has this chat template, and you call apply chat template to get the column, the appropriate column here. So this will then generate the appropriate column with the correct with the messages, with the prompt and the messages in this chat template format. So here's that Ginger template, which is typically used for ChatML. So once the model is formatted via the chat template, to run supervised fine-tuning is very simple with the TRL library. In the TRL library, you just import the supervised fine-tuning trainer. You specify your model, your base model. You can initialize it. You can define some training hyperparameters like the learning rate and the scheduler, and as well as the batch sizes and where you want the output to be, your resulting model to be. And then you define the trainer as the supervised fine-tuning trainer with the model ID, as well as the data set. We remember now the data sets are the chat templated versions of the data set. And then you can then call trainer.train. And essentially, this will take a few hours. And then you can, after which you will have a saved SFT model in the resulting output directory. Any questions here? Okay. So once you have a SFT model, one needs to perform alignment for some particular use case. So in terms of the steps, the process is again very, very similar to the supervised fine-tuning case. You essentially need to load a data set, you apply a chat template, and then run the DPO method on that. So the main difference, of course, is now your data set is no longer a prompt and a completion, but it's rather prompt and a chosen and rejected completion. So you need to have a data set that has this pair of prompt and chosen and rejected completions, which are your human or AI annotated chosen and binary examples. So once you have such a data set of prompt, chosen, and rejected, everything kind of the result. Everything after that is very similar to the SFT procedure. And again, as I mentioned, we also have a collection of such preference data sets as well under this link here for you to try out yourself. So at a very high level, and at the very least, the prompt, the data set will contain a prompt and the chosen response and the rejected response. And in our terminology of the loss that I was talking about, the prompt becomes the X, as you know, and the chosen response is the YW, and the rejected response is the YL. And this is what directly maps to our loss here. The other thing to note is that in terms of calculating the loss, I can calculate the log probabilities with respect to the winning response. So this prompt and winning response kind of independently, and the prompt and the rejected response independently. Independently here. Without these two branches kind of interacting with each other. It's only at the final loss calculations where these two things need to somehow interact. So as far as the model is concerned, everything can be independent. The other thing to note is that a prompt can also have, in many data sets, you have a prompt with many responses, where the response 1 is the most preferred response 2 is the second preferred, and so forth. So in data sets like this, we still need to make it into a binary data set. So what is typically done is that the prompt and the response one becomes the chosen response, and then the prompt and some random one here between 2, 3, and 4 becomes the unpreferred response. And you can also then have another row where you have the prompt and response one as the chosen, and then some other one as the unpreferred. And so you kind of have much more variety in some sense with respect to the rejected responses. In the multi-turn example, where you have a prompt and response and prompt and response, it is typically the very last response that is used for the preference for binarizing. So for a big tree of conversations, you have many different branches, and it's only on the very leaf of the branch where you can then select where you have the response and where you have the chosen response and the rejected response with respect to the chat. So for example, the Open Assistant dataset has a similar schema as this. It's a very big tree of conversations, and you have many different combinations of chosen and rejected responses. So in terms of applying those templates, we'll just tokenize them individually, right? And in our batch, then we will have always, our batch will be always have an even number of entries in our batch, because for each entry in our batch, we'll have a independent prompt and chosen response, and a corresponding prompt and rejected response. Remember, as far as the loss is concerned, I can calculate the loss with respect to the chosen and with respect to the rejected. It's only at the end where I need to subtract them appropriately, and they need to interact with each other. As far as calculating the loss with respect to the language model, that can be done independently in some sense. So the forward pass is only done independently through the model, and it's only at the end where you need to, that the model is made aware of the chosen and rejected belong in some sense to each other via the pair. Just because of how the loss is calculated, really at the end, with the difference between the log likelihoods. The difference between the pair, the log likelihood ratio, remember the ratio. So for the DPO method, applying the chat template to binarize data is again very similar to the SFT. The DPO trainer will, once you do that, now when you have the chosen and rejected with respect to the chat templates, the resulting data set will just work with the DPO trainer in TRL. So the DPO trainer in TRL can be used to do the preference tuning, and you provide it with the model ID. It's a model ID. You again provide it with the training arguments, and in particular, you need to provide it with the beta. Remember the beta that control the width between the margin between the chosen and the rejected, and as well as the loss type. Well, the loss type, because as I said, the DPO trainer implements the DPO method as well as many other variations of it. The original DPO method is the loss type sigmoid, which is just the default one. So you don't need to specify it, but just for your information, there's many other different loss types that can be given here via the loss type argument here. So if you provide it with just a single model, then the DPO trainer will make an initial copy of this model, which will be used as a reference model. Of course, you can give it a reference model explicitly, but if you don't give one, then this model will, the original version of this model will be given as a loss, as a reference model. And again, the resulting model after you do train will be saved in your output directory. So it's as simple as just doing that on your data. And remember, this data is the one with where we've run the chat template and has the preference, the specific columns for the prompt chosen and rejected. Right. Of course, the beta, as I said, is an important hyperparameter, and we have a blog post here where we've kind of done a sweep of the beta with respect to the different methods to show how this beta works, what the effect of this beta is on the downstream performance of these models. So have a look at that blog post if you're interested. So some tips when you go and run these algorithms are highlighted in this slide. Of course, beta itself needs to be tested from very small to very large. So if you want to do a scan of beta, then our advice in some sense is to sweep the smaller values of beta much more than the larger ones. The learning rate also needs to be much smaller than the supervised fine-tuning learning rate, and typically around e to the -7 is the go-to learning rate. So typically the batch size needs to be as large as your GPU can handle, but we find that there's a trade-off between the global batch size and or the batch size across your GPUs and the number of epochs as well. And so you just need to be, you need to also be careful on how large those batch size is with respect to if you're running it on multiple GPUs. Optimizers is an interesting question. The original paper of DPO was using the RMS Pro optimizer, but what we found was that Adam seems to perform better as an optimizer. We also found that the cosine scheduler is better than the linear one when it comes to the downstream performance of these models. Another interesting observation is that if you take your best SFT model and perform DPO on it, then it will not give you the best DPO model. Sometimes the worst performing supervised fine-tuning model will give a better DPO model on the same data set. So it's worth going over your whole, it's really worth going over your whole SFT plus DPO pipeline to get the best hyperparameter rather than using the best SFT model and then doing DPO on. Another observation with respect to parameter efficient fine-tuning, or LoRa, appears is that LoRa is essentially regularizes the model compared to the full fine-tuning setting. So with LoRa, essentially you don't deviate too much away from the original model, while with the full fine-tuning, it perhaps could be that it generalizes less than when you do LoRa. Is that okay? So those are some advices. So to demonstrate the property of LoRa on the right, for example, here is the evaluation with LoRa in green and with the full fine-tuning in pink. So this is green here is LoRa, and full fine-tuning is here. So as you can see, with LoRa, as you train, your evaluation loss, stays around 0.5, whereas with full fine-tuning, after a while, you start overfitting in some sense. Whereas the dotted lines are the training and are the training curves, are the training losses with respect to LoRa and full fine-tuning. So LoRa tends to be a better generalizer than full fine-tuning. On the right is again the accuracy metric of the test set, and here you can also see how full fine-tuning causes the accuracy to shoot up to 100%, meaning it's overfitting, while with LoRa it kind of plateaus to around 80% with respect to the evaluation metrics. Any questions here? All right. If you train with DPO, then there's a number of metrics that it's important that you log it, and one metric is to look at is the accuracy there, the accuracy metric. So you can predict the chosen and rejected rewards in a batch and check the number of times the reward for the chosen is larger than that of the rejected. And for normal training, this can go up to say 80% on the evaluation set. You can also look at the rewards for the chosen. Here's the rewards for the chosen. The log probability of the log ratio of the chosen with respect to the model and the reference model. That's this number, and the log ratio or the log ratio of the rejected here is this number. And the difference between them is this margin. This is this margin here. So you want this margin, of course, to increase over time. As you train more and more, this margin should be increasing, both for training and for testing, for evaluation. So training is the red, evaluation is the blue. So this is very important that things. Evaluation and metric plots like this mean that things are going well for your training. Some runs, of course, will not work, and so here you see here you see a run which is not so good. Here the accuracy at least goes up, but then it plateaus, and the margins are, where's the margins? Here are the margins. They're slightly above 0, but there's hardly any difference between the margins. So there's no separation in some sense between the chosen rewards and the rejected rewards. So this is a run which is kind of failed in some sense. And if we go back to the loss curves, we can see that of this failed run, the loss, we can see that during training there was a big spike in the loss, after which it became very unstable. So in this case, what happened was that the learning rate was far too high, and we were experimenting with the learning rate, and it was set far too high, which caused then the model to become very unstable and have very high these high spikes in the loss curve. And the reason the learning rate went up so high was because we had set the scheduler with too many steps, and so it was ramping up the learning rate very quickly and causing instability. So if we had, for example, the number of epochs was small, then such a situation would not have happened. But because we were logging it, we could see and diagnose such problems. Oops, sorry. Okay, so in the final part, I want to talk about what happens after fine-tuning. After fine-tuning, one needs to evaluate a model, and essentially there are a number of ways of doing that, and we recommend, in some sense, the empty bench benchmark as well as the alpaca eval benchmark. And the empty bench benchmark is a multi-turn dialogue dataset that tests things like reasoning, math, summarization, and it gives a score to the models between 0 and 10. So here's 0 to up till 10 is the maximum. And the alpaca eval gives the score between, gives a score which can, I think, go up to 50, I forget. And the other thing to remember is on the y-axis is a log scaled. So this is log scale. So internally, MTBench uses the GPT-4 to evaluate and judge the responses, and we've seen examples. So of course, then the GPT-4 is in some sense the best, it has the highest MTBench score, approaching 10. But we've also seen failure cases of MTBench as well. For example, MTBench will judge responses from GPT-4 as much higher in, for example, math question and answers, even though the answer is wrong, it will judge the response from GPT-4 much higher than a correct answer from another model. So, so the other benchmark, of course, is the alpaca eval, and here again, better models get higher values here. And so all other models kind of lie in this quadrant, and typically you want to be in this upper right quadrant. Any questions here? Okay. Another way of evaluating is to use human evaluation, which in some sense is like the gold standard of evaluation. And here you can use the LM-SIS chatbot arena, which essentially is a place where you can add your model, and then you're given 2 random models, and then you need to judge which of the responses from those models are better, and then those random preferences are used to then judge the models with respect to how well they do. So this, in some sense, is like where everyone tries to put their models for evaluation. And it's typically the proprietary models that are, at the moment, the best ones. Yeah. But of course, it's expensive and time-consuming, and quite a subjective kind of evaluation benchmark. The second one, as I said, is the MTBench, which is the LLM as a judge. Essentially, it's very cheap and fast to run. It has multi-turn support. Of course, it has many quirks with respect to the response length and how it grades mathematics and so forth. But still, it's kind of a systematic evaluation suite which tests a model's abilities in these specific areas like writing, role play, reasoning, mathematics, and so forth, and then returns such a nice visualization as well, using ChatGPT-4 as a judge. There's also model-free methods of evaluations. The 2 I want to highlight are mix eval and instruction following evals. They don't require a secondary model to run. They just ask the model you're testing for some specific questions and answers, and then those responses are then checked by heuristics to get some evaluation metrics. Okay. So here's a kind of a non-exhaustive list of these methods and their how to use them with their documentation, so that you can try them out yourself. The Open LLM leaderboard is also a leaderboard of language models. It's not typically chatbot focused, and sometimes at the moment, many models are kind of competing to be on top of this by maybe training just for this benchmark. And so the use of this benchmark is getting less and less relevant over time, but it's still quite a useful tool to kind of see which one is better than the other with respect to just general LLM capabilities. Finally, there's a very useful tool to observe correlations between the different benchmarks. So this is the benchmark correlation plot. And here, this is useful because you can see, for example, that empty bench has a 0.9 correlation with human evaluation. That shows, so here's empty bench. Let's find empty bench. Yeah, so here's human evaluation, and here's empty bench. You can see that it has 0.95 correlation with human evaluation. So it shows that empty bench is really a good tool if you want a proxy for human evaluation. Even though it's not a substitute for it, it's still a much cheaper way of evaluating than getting humans to evaluate your model. And so with this kind of plot, you can see how different benchmarking methods can be made, are proxies to other ones via these correlations. So it's again very, very useful.